Good morning. My name is William Morley and I will be presenting my report on visual place recognition for loop closure detection in GNSS denied UAV navigation. UAVs rely on the Global Navigation Satellite System for localization and path planning. However, satellite emitted signals are weak, leaving them susceptible to threats like jamming and spoofing. These threats precipitate mission failure and endanger high-value assets. To address this problem, the following objectives were established. First, to create an analysis-ready dataset. Second, to evaluate GNSS-independent navigation systems. Third, to develop a VPR pipeline for resource-constrained UAVs. Convolutional neural networks act as a powerful dimensionality reduction tool. By removing the final classification layer, the network's convolutional layers act as feature extractors, producing a compact feature map. An aggregation layer, like NetFLAD or global average pooling, then compresses this map into a single vector for efficient image comparison. Traditional navigation systems, such as inertial navigation and visual odometry, both suffer from drift, the accumulation of uncorrected errors. Visual simultaneous localization and mapping mitigates this drift by building a map and using loop closure, the re-identification of a previously visited location, to correct the vehicle's predicted trajectory. However, VSLAM fails at higher altitudes due to a lack of scene depth cues. These limitations led to the development of visual place recognition techniques. VPR systems use CNN backbones with a final aggregation layer to generate compact scene descriptors. Loop closure is achieved when a query's extracted embedding is sufficiently similar to an embedding in the stored database. While numerous VPR publications exist, this report identified two clear research gaps. First, current systems are not tested at high altitudes, specifically exceeding 2,000 meters, which is a practical altitude band for intelligence, surveillance, and reconnaissance applications. Second, existing systems rely solely on the closest match in global feature space and do not employ local features to refine these potential candidates. The data was provided by Molcor from 2 missions. Each mission included 2 GoPro videos from the wing-mounted cameras and 1 telemetry file. The GoPro metadata extracted via GPMF parser revealed commercial-grade IMU sensors. The telemetry files were inconsistent and required varied pre-processing techniques. The most critical issue was the lack of a consistent timeline, which required synchronizing and evaluating 2 potential time candidates for each flight. The GoPro data streams also required extensive pre-processing. Due to time constraints, I will only discuss the power spectral density analysis and filter design. The PSD was estimated for all IMU channels using Welch's method. The plots show a clear distinction between 2 components. First, high power at low frequencies, corresponding to the UAV's kinematics. Second, distinct high-frequency peaks are present across both flights and sensors, likely suggesting the platform's vibrational signature. This demarcation between low-frequency kinematics and high-frequency noise justifies a low-pass filtering strategy. A 4th-order Butterworth low-pass filter was applied. The cutoff frequency was selected by maximizing the cross-correlation between the 2 camera sensor channels. Kinematics should be correlated while noise is uncorrelated. The plot show the raw versus filtered signal at approximated takeoff. The filtered signals were crucial in identifying the takeoff event, which enabled synchronizing to the telemetry data. Due to time constraints, telemetry pre-processing cannot be detailed in full. Flight 1 is detailed in the slide, while the challenges of Flight 2 will be discussed. For Flight 2, 2 critical data issues were fixed: an hourly timeline reset and duplicate consecutive positional samples. 2 timeline candidates were constructed and evaluated: count time, in blue, based on the median sampling frequency, and shifted time, in red, which accounted for the hourly clock resets. The duplicates, likely from a slower GPS polling rate, were resolved. For moving samples, a 3-step process was used: identifying duplicate pairs, replacing the second sample with null, and then linearly interpolating its value using the first and the third. This approach successfully removed over 45,000 duplicates, with a negligible RMSE of just 3.72 meters. The timeline candidates were validated by matching video frames to satellite imagery. As the figures show, Flight 1's candidates failed. Flight 2's shifted time was consistently accurate, Reliable synchronization is critical. The unresolved timing issues in Flight 1 led to its exclusion from further analysis. The flight plan assumes that upon detecting GNSS denial, the UAV performs a 180-degree reversal. This profile resulted in two suitable segments, Cruise 0 and Cruise 1. As the table shows, GNSS is assumed to be denied for the turning and inbound operational phases. Cruise 0 is low altitude with visually repetitive terrain and a wide visual baseline of 1,800 meters, complicating VPR. However, Cruise 1 was captured at over 2,000 meters, exhibiting visually distinct features and a narrower baseline. This dataset is an accurate representation of I-star operation. From the UAV payload, local and global features were extracted. Several lightweight CNNs and aggregation layers were benchmarked, as illustrated in the table. The NetFLAD aggregation layer was rejected due to its additional storage overhead, rendering it impractical for extended missions. MobileNet V3 with GAP was selected as the optimal backbone, offering the best balance of low latency and dimensionality reduction. The system was calibrated using the outbound segment. A similarity threshold of 0.92 was selected to trigger the VPR pipeline. Next, K for the K nearest neighbors search was set to 3. As the graph shows, this achieved a 99.4% recall while minimizing the local refinement workload. For the refinement phase, BF Matcher was selected over FLAN due to its lower latency. Finally, an inlier threshold was set to 50. This rejects the loop closure if the top candidate has insufficient inliers. For the position estimation pipeline, two systems were benchmarked. For the INS, two sensor sources, the filter gyroscope readings and camera orientation quaternions were evaluated, as well as two speed models using the average speed of the outbound samples and the ground truth speed. For the VO system, models for C1, C2, and an average of the two were tested. The cosine filter alone resulted in a recall at 1 of 100% for the sparser breadcrumb databases. However, the high maximum error across all systems shows the inlier threshold was too low. Even when the pipeline found the correct breadcrumb, the match should have been rejected by this threshold, which would have reduced this max error. The densest database, with alpha set to 0.75, had a lower mean error, but 10% of the pipeline's accepted queries were false positives. This local feature refiner failed here, also hinting towards too low an inlier threshold. Therefore, the area-based dropper with alpha set to 0.5 was selected as the best compromise. It correctly identifies the best candidate 100% of the time after the cosine filter alone, and detects loop closures for over 12% of all queries. This achieves a low mean error appropriate for high-altitude I-star applications. Further, we need to investigate the breadcrumbs themselves. As you can see, the breadcrumbs with 0 matches aren't failures. They were successfully filtered by the similarity threshold due to the large viewpoint disparities. The local feature refinement phase also successfully rejected matches that were further away from the breadcrumb, thus improving localization accuracy. For the INS, the filtered gyroscope signal shown in red clearly shows the least drift, outperforming the quaternion source shown in green. However, both are highly dependent on the speed model, which significantly impacts their reliability. For the VO, performance is terrain dependent. On the homogeneous terrain of Cruise 0, it fails completely. On Cruise 1, the average model, in pink, appears accurate, but this is a misleading coincidence as it's simply compensating for two poor fits from C1 and C2. For the position estimator, the filtered INS was the most robust. However, all systems drifted, confirming the need for a relocalization strategy. The VPR pipeline proved an effective solution. It's resource efficient, reducing storage by nearly 99%, and computationally efficient, executing in under 100 milliseconds. The local feature refinement also succeeded in improving match quality. For future work, I recommend firstly applying a sensor fusion approach, possibly with a Coleman filter, to the INS and VO systems to mitigate their weaknesses. Secondly, using the VPR's geometric refinement step to recalibrate the INS's heading estimate. And finally, using UMAP for terrain detection, which could determine which position estimator to use in real time. Thank you for watching my presentation.